My name is Sophia Schramm, and my project title is Boe-Bots plus sensors plus algorithms equals maze navigation. The relevance to society of my experiment is summarized in this slide. My problem is, can robot sensors successfully navigate a Boe-Bot through an increasingly complex maze if they are calibrated and integrated successfully? And my hypothesis is, if Boe-Bot and sensors are calibrated and integrated successfully, and algorithms are designed and revised, then sensors will be capable of navigating a Boe-Bot through an increasingly complex maze. My procedure is to assemble the Boe-Bot, download the PBasic software programming and development application, test the program, attach the wheel service to the Boe-Bot, calibrate and integrate the sensors, choose the best algorithm, create the maze, test the individual sensors, combine algorithms with the best two sensors, test the final algorithm and sensor combination, and then refine and evaluate. This is a picture of the integration motherboard and the microcontroller. The microcontroller is the Boe-Bot's brain, and the integration motherboard is where all the sensor wires get connected to the Boe-Bot. These are the pictures of the two types of servo motors used in my project. Servo motors help rotate the Boe-Bot's wheels and the ping sensor's eyes. The first sensor I tested was the whisker sensor, one of the simplest sensors evaluated. The second sensor I evaluated was the infrared sensor, which was another simple sensor. The third sensor I evaluated was the ultrasonic ping sensor, which was the most advanced of the three sensors. My last experiment was on the infrared and the ultrasonic sensors combined. The first phase I went through was the servo and sensor calibration. I needed to perform the calibrations to accurately define the duration arguments for all the servos and to calibrate all the sensors. Duration arguments are what the PBasic programs use to send the appropriate pulse train to all servos. A pulse train is a series of pulses that keep repeating. These pulses define the speed and direction of the servo. This graph shows the rotational velocity versus duration arguments for the right servo. And this graph shows the rotational velocity versus duration argument for the left servo. With this information, I then defined the navigation behavior as a function of duration arguments summarized in this table. These were the building blocks for my algorithms. Moving on to the infrared calibration, I had to define the maximum detection distance for each of the series resistors using the integration circuit. The final part for phase 1 was to define the duration arguments for the ping sensor. This next picture shows the wooden maze I created for my Boe-Bot to complete. Phase 2 began with specialized algorithm development for each of the sensors evaluated. For the simple sensors, I used the left wall algorithm. This allowed the Boe-Bot to move in a limited forward excursion after forcing it to constantly hit the left wall. To meet the objective of navigating complex mazes, a more advanced algorithm with the advanced ultrasonic sensor was designed and evaluated. The pseudocode for the more advanced algorithm using the ping sensor is shown in this slide. These two tables show the results of the test trial phase. This graph shows the completion time for each trial. In conclusion, my hypothesis was proven for all sensor cases. Furthermore, with the success of the combined sensors, Boe-Bot is ready to navigate mazes of greater complexity.